I'm very sorry I had to cancel Tuesday's class before an emergency event in my family. And before the class begins, I have a few things to change and I would like to discuss with you. The first thing is about the quiz. The system manager of ILMS told us that to take the online examination, students are not able to upload files. So you are not able to scan or photo your answers and upload the answers to the system. It's very unfortunate, so that we have to change the plan to take the quiz. So we will go back to the traditional way. So we have to find a time slot to take the quiz examination. And I think the initial proposal to take the quiz examination at the noon from 12:45 to 1:15. I'm not so sure it is still appropriate for you because that it will shorten or squeeze your lunchtime. So maybe we will discuss an alternative time. And this is one thing. The second thing is that because that in addition to the Tuesday class I canceled, I also need to cancel the class next Tuesday. So I have to make up the lectures in some time. Okay. And at the beginning, the first week, I have to go to in my schedule, I have to go to the United States for a conference. So in addition to November 1st, that is our first examination time. So I have to cancel the class on November 3rd. So I think we have to make up the lectures for 3 times. And so the quiz. So the quiz time, we have to discuss. And the second is that the class makeup. And okay. I propose, this is my proposal, and you can. So how about on Monday? From 6:30 to 7:30 p.m. Is this time slot convenient for each of you? So we will have the quiz examination here, and from 6:30 to 7:30 for 1 hour. Yes, please.
下午的时间。大约下午的时间。
up to 6:30. So you need the dinner time, right? So I have 7:30 to 8:30. Is that okay? Okay, so this is the regular schedule. So we will have a quiz basically every Monday. Okay, and from 7:30 to 8:30. And I estimate that we will have maybe 14 to 15. I have to recount it, all right? quizzes in this semester, and I was like the highest 10 quiz score for each student, right? The highest 10, all right, scores for each student to take an average for your semester quiz percentage, because we have 25% for quiz examinations. Okay, so occasionally you have emergency things to do. I think you can sometimes be absent from the quiz exam for 1 or 2 times. Okay, is that reasonable for you? Okay, so we fix, right? So we fix the quiz time Monday, 7:30 to 8:30 p.m. Okay, and basically in this classroom. Now we have 3 classmates at time. So my proposal is that it's October 3rd. It's also on Monday. So now we shift from to okay, and double 10. I think this is only a very short holiday, so is possible for you to come back. Double 10 is a holiday, it's a national holiday, but this is my proposal. We can change that, right? So let me write down the proposal. Okay, so basically the makeup class will be right after the quiz examination. Okay, so yes, please. Oh, PM, sorry. You like AM? Yeah, I'm okay. No? Oh, wow. Okay, so it's PM. So that is the 3 days. This is proposal. So no problem with me. Okay. So we fix the schedule. So we solve 2 difficulties. Thank you very much. Yeah. It's all because of my personal reason, and so I'm truly sorry to make those changes. And this one, this pretty hard we cannot do, so we have to, because I will ask the ILMS system to make some changes so that, yeah, maybe in the future you are able to submit your solutions by uploading the scanning solution or photo solutions. Okay. Okay. All right. So we will continue discussion. Oh, so by the way, the first quiz will be next Monday. Okay, this time. And okay. All right. So I think this last Tuesday, we talked about the separable method to solve first order ordinary differential equations. And but sometimes we face ODE. So let's take an example which is not separable. Okay. Okay, so see this example. It's very hard, right? And actually, it's impossible to do any algebraic manipulations so that the ODE becomes to be separable. Okay, so this is a non-separable case. So, but so in certain non-separable ODEs, including the example above, or okay, so including this example, we can turn it into a separable one by a suitable transformation. Okay, so the case is that except if we have an ODE in explicit form, like this one, so y prime is equal to a function of the ratio y over x, okay, where f of u, f is the function, is differentiable. Okay, on open interval. Okay, so suppose we have such a first order ODE, okay, and with f of u differentiable. Then the suitable transformation can be, so the same thing as suitable, like we define u as the risk ratio. Okay. So of course, because y is a function of x, so u is a function of x. Okay, so we make this transformation. Right. So then we know y is equal to u times x. Okay, u times x, and so this implies that by taking the derivative with respect to x, so applying the multiplication rule, so we have u prime x plus u, okay? Because the derivative of x with respect to x itself is 1, so we have this. Okay, now, so y prime, so now we replace the left-hand side of the ODE by u prime x plus u. So this is, so our ODE becomes, okay, so we have u prime x plus u is equal to f of u. Okay, because y over x has been defined to be a new function, so we have this. Okay, and so now by some algebraic manipulation, we find that okay, So we find an ODE which is separable. Okay, so you can see that. Okay. So once you encounter an ODE in explicit form like this one, by a suitable transformation, we end up with a separable. So now we can apply our previous method to solve this separable ODE. Okay. So we go back to our example. Okay. So now for this example, 2xy y prime, which is equal to y squared minus x squared. Now we divide both sides by 2 times xy. So we have y prime equal to y squared 2xy minus x squared 2xy. Okay, so this comes to 1/2 times y divided by x minus 1/2 times x divided by y. Okay, and it is obvious that this is equal to f of y of x here. Okay, and what is the f function? F of u is equal to half of u minus half of 1 over u. Okay, so you see that here we have that one. Okay. So now so it is in this form, and by our previous method, this comes to we can transform this non-separable ODE into this separable one. So so now the transformed separable ODE is so we have u plus x plus u equal to u minus 1u. Okay? Yeah. So this is so we start from here. It's much more easier. All right. So now returns to u plus x is equal to so we remove this here, so this comes to minus u squared minus 1, and here is 2u. Oh, I'm sorry. First minus minus. Yeah, I'm sorry. So by algebraic manipulation, when we move this term to the right hand side, we have this one, and so we have 2u 1 plus u squared, and the u prime equal to minus 1 over x here. So now we are well prepared to solve this separable ODE. Okay. So now So we have equal to constant. Take C star. So this is just standard procedure, right? So we have C square. Okay. So you can see if you do the derivative by chain rule, the derivative of this logarithm becomes to the integral, right? When it is integral. So and for this one, it's easy. It's also okay. We don't need to put the absolute value sign because 1 plus e squared always positive. So it's not necessary to put the absolute value sign. But here we need to put the absolute value sign. Okay. So plus C star. All right. And so this is equal to, right? So now we take the exponential functions. We find this is 1 plus u squared becomes to x and then c here. Right. The reason is that because we have plus and minus sign. So, but exponential of c star is always positive. All right. So generally we have if you I can do it step by step. So this is equal to x, for example, exponential c star like this one. So you can have okay like this one, and finally you have this. Is that okay? So c is basically equal to plus minus e to the c star, because e to the c star is always positive. Okay, but because of the absolute sign, you can have plus and minus. So the whole thing, this is a constant, and the c here. All right. All right. So c is r. Okay. Now we haven't finished yet because what we want to find is the y function satisfy the ODE. So remember, y is u is equal to y over x. So we have 1 plus y squared x squared. Okay, is equal to c over x here. Okay, so this turns out to be x squared plus y squared is equal to c times x. So now you see it's an equation of a circle, right? So this equation defines the function y implicitly. Okay, so this is an implicit definition of the function y, and so you can write to the equation in a standard form. Okay, so we see that there is a circle, all right? An equation of a circle on the plane, in the plane, and the center of the circle is 2 over c of 2 and 0. And what is the radius of the circle? The radius of the circle is the absolute value of c divided by 2. Because c can be negative. Okay, c can be negative. So this is the answer. Okay. So you see that the equation, this differential equation, actually describe the circle. Describe a circle in this plane. Okay. Any questions? Okay, and in the exercise of these sections of the textbook, provide several different types of non-separable ODE, and it suggests some transformations for you. to transform to turn a non-separable ODE to a separable ODE. So you can do the exercise and to get more experience. Okay, so it depends on these things. Thank you. Any questions? Okay, so if no, now we go into the next section. Right, we learn from calculus that if a function, okay, u of xy, okay, so it's a function of two variables, okay, has continuous partial derivative, okay. Then it's differential also called its total differential. Okay. It's this one, du. Okay, defined to be the partial derivative of u with respect to x, and dx, plus the partial derivative of y of u with respect to y and dy. So we call this as the total differential of this function of two variables, x and y. Now, if we consider the equation, okay, this equation describes a curve in the plane, okay, in the xy plane. So it describes a curve. C is a constant. So if we consider such a, and then, so consider points on the curve described by this equation. Then we know that the total differential is equal to 0. Okay, so that is the it's very obvious, right, from this equation. So let's take an example. Suppose u is equal to x plus x squared and 1 cube, which is equal to c. Okay? So suppose we consider a curve described by this equation. So c is just a constant. Then du comes to 1 plus, because we first take the partial derivative with respect to x. So this is equal to plus the partial derivative with respect to y. So this is 0. So this is equal to 3 x squared and y squared. Here. Okay. And this should be equal to 0. And should be equal to 0 for any points on this curve defined by this equation. for a given constant C. Okay? And so now we end up with a differential equation. All right, so this is equal to y prime. Okay. So y prime actually is dy and dx. Okay. All right. So this comes to minus 3x2 y2 1 plus 2x y cubed. So now we end up with such an ODE. So which is an ODE? And can be solved straightforward. If we know such an ODE, right, is obtained through this procedure, namely that it is from the total differential of a function U of x. If we know that, then actually the solution, the y function of x, the solution actually is defined implicitly by this equation. If we think quickly, right? So actually, this is an equation which defines a function y, all right? And y implicitly. Okay, so this is the idea, but a question is that initially you are given an ODE only, right? And nobody tells you whether it is from a total differential. You don't know initially. So you have to have the method to make your judgment. Okay, to make your judgment. So we will develop such a technique to distinguish whether a given ODE is from a total differential of a certain function U. Okay. So now we first give the definition. The first order ODE. Okay. Right. So this is the first order ODE. Okay, taking the form like this one. Okay. So it's so actually. Or you can say this n xy prime equal to minus m xy. Okay. So many first order ODE can be written in this way. Basically, you can write in this way. Okay. And this is just a standard form. This is standard form only. Okay. Sometimes if you think about here, because y prime, things y prime actually is dy dx. So this first ODE also can be written as m xy dx plus n xy dy. Okay. So they are all equivalent, right? You can write first order ODE in this form, or in this form, or in this form. They are all equivalent to each other. Okay? Because y prime actually is equal to dy over dx. Any questions? If you have any questions, please let me know. All right. So now if we have the ODE and we say, so this ODE is called an exact differential equation. Okay. If with the differential form, okay, so actually this is called the differential form. The differential form m xy dx plus m xy dy. This difference is exact, i.e. The mxy is equal to the partial derivative of the function u with respect to x, and n xy is equal to the partial derivative of y with respect to y for some u xy. So this is the definition of an exact differential equation. Okay, so if we know this is true, so when we see first order ODE, okay, like this one, we turn it into differential form, like this one, okay, and the check the differential form is exact. Right, means that we can find some function u of x such that m of xy is equal to this partial derivative, and n of xy is equal to this partial. If we can find such a u function, right, then it is exact. And so we call this is 1. So then 1 can be written, okay, as du. Okay? So if this is true, then 1 can be written as du equal to 0. Okay? And from our previous discussions that if the total derivative is equal to 0, so that's and the general solution for this ODE is u of xy equal to a constant c. So we have a parameter c here, which is called an implicit solution. Okay. So once we check an ODE is an exact ODE, then the solution, a general solution, is immediately obtained by the function u, this function, and put a constant c. Alright, so this equation actually gives you the solution y. for the original first order protein. Okay. So now the major task to solve an exact differential equation is to check whether this ODE is exact. Okay, so that's the major step. So now, so how do we know, right? How do we know this is exact? How do we know? Now, necessary and sufficient condition is, so now we provide the necessary and sufficient condition. Is that you can take the partial derivative of m with respect to y. Okay. And you can take the partial derivative of n with respect to x. Right? And you must have equality. Alright, so this is the necessary and sufficient condition. The proof is quite simple for necessary condition, but it's not so trivial for sufficiency. Okay, so I just give you necessary, the proof of necessary condition. So now, so this means that if m is exact, then by definition, if this is exact, by definition, m of y is equal to the partial derivative of u, right? Then there exists, I have to say, exists. Maybe. So then there exists a function u x y such that m of x y equal to and n So now, thus, so now we take the partial derivative of m with respect to y. Now we have the second partial derivative of u. Okay, and the partial derivative of n with respect to x will come to another partial derivative of u, the second partial derivative of u. Right? So now, okay, so now we have Now here, to make sure, because these two mixed second partial derivative, actually they are different. But if we have one condition, then these two mixed second partial derivatives of u are equal. Do you know what is the condition? Continuity, huh? Yeah, very good. So you already learned that. So the necessary and sufficient conditions is that so we have to give a condition for that. So now a necessary and sufficient condition is this one. Okay? And where? Okay? So we need continuity of these two partial derivatives. We need that. Okay, we need the continuity. So this continuity to make sure that we have equality here. Because this is continuous, so this is continuous, right? So they are equal, right? So this is continuous. And because this is continuous, so this is continuous. So these two mixed second order partial derivatives. Sometimes I omit the discrepancy on a certain open interval. Actually, if I don't say anything about that, I do mean that it is continuous on a certain open interval. This is sufficient. You don't need to say that these two functions are continuous on the whole real line. You don't need to. Just a certain open interval. It's okay. So this is the necessary condition. Any questions? The reverse part is a bit non-trivial. So right? It is covered in section 10.2 of the textbook. So it is actually in chapter 10, but we will not cover chapter 10 because it's about the calculus on several variables. And I think some of the material already covered in calculus too in the last semester. Like Green theorems, Gaussian theorems, okay, Stokes theorems. Did you learn that last semester? Green function, Green theorem, Gauss theorem, divergence, curl, such of things. No? What? Oh wow! Don't know that. I'm so surprised. I suppose that topic should be covered in the second semester of the calculus course. Okay, if you don't know anything about the Green theorem, Gauss theorems, or Stokes theorems, I recommend you to read chapter 10. You know about that of the textbook. Because you do need this kind of things to learn electromagnetics. Okay? I think most of you will take this course next semester. Electrical magnetics, you know that? EM theory. Okay, so so we have a tool. Basically, this is very simple tool, right? You just okay. So let's take an example. Oh, I'm sorry. We have to take a break right now. Okay, so take a break and come back 2 times.